Hey guys, today we are gonna have the real life problems of the circumcenter. The real life application problem is a triangular park wants to place circular lines on edit corners, all at the same height. The park side is 95, 104, and 77 meters. Three lamp types are available. First lamp is radius 50 meter, cost $1,500, and annual energy cost is 510 kilowatt. Second has radius 55, cost is 1800, and annual energy cost is 735 kilowatt. And the lamp 3 is a radius 60 meter and $2,400, and annual energy cost is 980 kilowatt. So which lamp should be chosen to fully illuminate a park while minimizing cost and energy consumption? So our approach should be in this way. So let's check the scenario. What is it? There's three lamp posts placed at the corners of a triangular park. And what is the goal? Determine the minimum lighting radius to cover the entire park, of course, minimizing the cost. And methods to solve, we have three methods. First one is the circumcircle formula. We calculate the circumradius, and according to we are going to decide which lamp types are going to pick. Second, coordinate geometry. So this is a little bit harder, but there's a way to solve it. And the third is GeoGebra. That is I think is most easiest and visual dynamic construction measurement we are gonna use. So, and at the end we are gonna ask why the circumcenter ensures full coverage, why we don't have other centers. Okay, method one is using this circumcenter formula. First, for finding this, we find the semi-pyramid. We add the all sides and divide by 2, which is 138 meters. And then by using Heron's formula, we find 3508.15 square meter, the area. Then by using the circumcenter formula, which is R equals 8 times B times 0, 4 times the total area, we find the circumradius 54.21 meter. Method 2 is using coordinate geometry. And first we place the triangle on the coordinate plane, A, B, and by using distance formula we can find C, which is 21.8 and 70.9. Then we find the midpoint of the sides and we draw the perpendicular bisectors by using their slopes. And the perpendicular lines intersect at a point which is the circumcenter. This is 47.5 and 26.1. And finally, by using distance formula from the origin to circumcenter, we use this formula, we can get the same circumcenter distance, which is 54.21. The last one is using GeoGebra. We construct the triangle by the length. As we see here, first we construct the triangle with the vertices, exact length side, and then we construct the perpendicular bisectors, and we label them. As you see, O is our circumcenter, and then we measure from circumcenter to the vertex. Vertex is as 54.25, automatically GeoGebra calculates, and we draw the circumcircle, which we just want to see how it is, and then we try to use those lamps diameter, like 50 meter radius. So if the lamps are here at the corners A, B, C, so it's radius 50 meter, and the illumination area is this, and the C is here. So totally, as you see here, there is some place, some spot which not totally illuminated. So this is a like safety problem, and also doesn't fully satisfy our result. So let's check 55. As you do this 55 and cover everything, every single part of this triangle part. So this is the cheapest and satisfy the total area, and uh, we can select this. The 60, of course, that is more coverage, but it is expensive. No need to pick that one. Technically, for geometrical result, we can select this one. So let's try to visualize this on GeoGebra. I mean, I did this in the past before this class, and now I'm gonna show you how we do this on GeoGebra. Okay, let's create this. First, I'm gonna go to line segment with a given length. So my length is 104, one side, and let's make it a little bit bigger. And I'm gonna construct the circle radius, which is 95, and the other is gonna be 77. First thing first, I'm gonna construct a triangle. So this is my intersection. So I use line segment, and okay, now let me hide the circles, this one and this one. Okay, my circle is here. Let me check the sides. 95, 77, and 104. Yes, that's right. That is what I want. Okay, now second part, I'm gonna find the perpendicular bisector. So this one is my first bisector, this is second and third. So this intersection is my circumcenter. We're gonna prove it, and I make it like, instead of D, let's make R, or D, let's make it O, and let's hide this part. This one, and this one, I hide them. Okay, now this is my triangle. Now let's construct radius, which is this center to vertices, and I'm gonna check whether dimension is okay. Yes, as a 54.21. So that is exactly what the previous methods gives us. Okay, we can use circle, and we just can see 54.21 exactly as is the circle pass through the vertex, the vertices. Okay, let's go back, and now I'm gonna try this lamp radius. This is my figure. Okay, let's try for 50 and 50 meters diameter, and this is first 15, second lamp, and a third lamp, which is 50. As you see, this region is not illuminated. So this is a safety concern. So of course we are not going to pick this one. It is cheaper, but we cannot use this one. Let's try to use 55. Since the radius is 54, of course, it is easy to see 55 will work, and we're just gonna make a visual proof. And as you see, if you zoom in, as you see, there is no uncovered area. So every single point is covered, and we can say it is really good decision to select this one. It's cheaper than the other one, and it has less energy consumption per annual. So this is my solution, and of course we are going to select the second one, which radius is 55. Okay, That is the first this question. But let's think about if we have a rectangular region, what can we do? How can we work on this? Maybe we can use the opposite vertices to join them, and we'll have two separate triangles. Then we can find the circumcenter of H, and then we try which circumcenter is greater. Maybe we can use that one. That is going to be your real life work for the next week until the Sunday. I'm going to ask this for the next Monday. Thank you guys for this. Let's go ahead and finalize the class.